that's how it is. So basically, I do hope that there is a possibility of making of some results that might have its significance if you want to design quantum machine learning on the chain of coupled quantum dots in a semiconductor. Okay, so first of all, I will talk about quantum mechanics and classical statistical physics very briefly, and then I will show how to move from a quantum tight binding model to classical physics model to epidemic model with a chain of mathematical equivalent steps. So there's possibility of going back and forth. All right. So first of all, in quantum mechanics, we have quite a few distinctive features that are only possessed by quantum mechanics. So there's a superposition of states at the same time. So this is being used in design of new quantum computers that have incorporated massive parallelism of processes. So all these processes are ongoing in parallel before the measurement is taken place. And once the measurement takes place, we have no longer this parallelism. Usually by strong projection, by so-called strong measurement, we project on one among n possible quantum states. So there's superposition of states. Obviously, there are some discrete values of eigenenergies that are also present in quantum mechanical system. There is a presence of entanglement and local correlations. So this is the most pronounced by so-called Bell states. So basically, we have a correlation. So when we have two particles that are entangled, or two quantum objects that are entangled, when we make a measurement on one of this object, this measurement affects the physical state of another object infinitely quickly. And the second object can be as far away as it is possible. So basically, we are talking about spooky action on the distance. That's how it is being named. So those entanglement type of states are quite, how to say, typical for quantum mechanics. Still, there's during Jarek Duda seminar, there is discussion of some analogies of such states with classical physics, as some vortices in fluid and so on and so on. So there's also quantum coherence. So the given quantum state possess the aforementioned properties when it is in a quantum coherent state. And this due to interaction of a quantum state with external environment, this coherence can be lost. So usually this coherence of a quantum state is not lasting too long. In case of quantum dots in semiconductor, we have the values of nanoseconds of quantum coherence, quantum coherent time. In case of superconductors, there are quite recent records that are beaten. So this is in microseconds or sometimes in milliseconds. And in case of NV centers in diamond, there are some records beaten. So it was shown that NV centers in diamond there is a possibility for quantum information to be stored in the range of seconds if the system is being cooled down to low temperatures. And still, NV centers in diamond have a quantum coherence time in milliseconds when the experiment is being made at room temperature. So this is very prominent feature. So this makes NV centers in diamond a candidate for a kind of quantum information processing at room temperature. So there is ongoing research in this direction. This is not topic of my presentation. Still, this issue shall be mentioned. Okay, so this is as far as I can tell about quantum coherence in a brief way. Then there is a quantum measurement and destroying of a quantum state by a measurement. So this is a postulate of quantum mechanics that measurement conducted on a quantum system is always in relation to the interaction of measurement apparatus with a quantum system. So there's a projection of a of quantum state, that it's a superposition of n states into one state. Right. So furthermore, this measurement procedure also can be conducted on the classical systems, but in classical system, the usually measurement in most cases can be done as a perturbation of dynamical state of a classical system. Those analogies in a very detailed way are very well examined by Dr. Adam Bednarz from University of Warsaw. He works on such analogies very much. And okay, so there's of course no non-cloning and no deleting theorem in quantum mechanics. There's also no cloning theorem in a classical physics. There was some proof that one dynamical state of classical physical systems cannot be fully being copied to another classical physical system. This was discovered in 80s, very many years after. So a few years after the no cloning theorem was formulated by Jurek. And there's of course path integral approach that takes place in a quantum mechanics. Still, a kind of path integral approach is also being expressed partly in classical statistical physics. Okay, so there are features of quantum mechanics. Obviously, there are famous path integral approach introduced by Feynman. So we have Feynman diagrams and so on. So, okay. So as about classical statistical physics, so there are certain analogies of classical statistical physics with quantum mechanics. We can basically say that that statistical ensemble is attached to one quantum particle. That's how it is. There are some books on. Those analogies are quite well established in literature. I'm just thinking about the name of physicist that is somehow. I need to refresh his name, and maybe I will mention you later. So yes, so there is also path integral approach in classical statistical physics. So if we have a boat on the lake or on the sea, this boat can drift from point A to point B, and there are infinite number of paths of drifting in certain time interval, and so it is. But still, at a given time, the quantum system can only evolve at one path. So there is no parallelism at the same time. And of course, there is also stochastic determinism in classical statistical physics. So also we can say there is stochastic determinism in quantum mechanics. And also, obviously, there is intrinsic noise that can be also derived that is present in statistical physics. Somehow we can also say there's intrinsic noise in the system, in the quantum systems of few interacting particles. All right, so there were main features of quantum mechanics being presented in a very short way, and main features of classical statistical physics. And now I would like to this is very preliminary slide, so I will just briefly mention a few things. So basically we have a Schrödinger equation, and that is written here. So we have that Hamiltonian, which is essentially as the classical mechanics is a sum of kinetic and potential energy. So Hamiltonian acting on a quantum state gives the dynamic of change of this quantum state with time, and then we can also this is also equivalent way of writing this in terms of Schrödinger equation. So this is time-dependent Schrödinger equation for one particle, and obviously we can write such type of equation as one is being can have analytical solution in such formats given here. So here we have Hamiltonian operator, and so this is exponent of Hamiltonian operator that can be matrix and so on and so on. So there is obviously there is a condition for normalization of a wave function. So there is a probability of finding the particle in the whole space, and so there is a probability of density probability density that it can be derived directly from quantum mechanics, and there is term that is real term and imaginary term. There are two terms of wave function. So basically, we can say that if we have these probabilities, we can have a sum of two probabilities. One is related to a real part of imaginary, a real part of wave function. So this is the first one, and the second one is the imaginary part of wave function, and the sum of these probabilities is observed probability. That depends on time. So obviously, this is textbook kind of a slide. Gives a very general view on dynamics of a quantum state, and this description is being kind of described for isolated quantum system. So then the system is not interacting with external world. Obviously, if you want to make a measurement, or if you want to set up the state of qubit, we need to have non-zero interaction of a qubit with its environment. With an environment around this, and if we take into account the presence of environment without full knowledge of the whole system Hamiltonian, we are dealing with dissipation processes in a quantum mechanics. So essentially, our matrix, evolution matrix, is no longer Hermitian in such type of case. So this requirement is not being fulfilled. Yeah, so description of dissipation in quantum mechanics is usually a bit tricky, and it's also a bit phenomenological, I would say. It's not a fundamental, but still it can be grasped by real experiments. All right, so this is very general slide. All right, so basically for last 2 years, I was interested in the systems of coupled quantum dots in a semiconductor. So the purpose of my interest was creation of models that can be useful in the implementation of quantum computer in a CMOS technology. So simply, if you buy a new computer, what you have is you have a field effect transistors. So you have a source and drain into regions, and you have insulator material that is being placed at certain places, and there are gates with certain voltages that are applied to those gates. So basically, by setting proper voltage V2, you can tune the connectivity between two quantum dots, quantum dot A and quantum dot B. And then you can control. So if you inject one electron here to a quantum dot A, by setting proper voltage, you can create a barrier between two quantum dot areas, or you can lower this barrier so this electron can move more freely. In any case, there are tunneling processes that are taking place. So basically, this device is can be very narrow. So recently, so there is so like you buy new computer. Usually, you have this channel length in the range of 10 nanometers, which is more or less like 100 atoms on this length unit. And in the most recent technologies, there's only 3 nanometers channel length. And so this is a very amazing result. So you can imagine how big gradient of electric field is if you apply voltages in range of volts, and there is only 3 nanometers of a distance. So basically, you can even observe relativistic effects with a movement of electrons. So basically, this scheme turns out to be very useful if you are thinking about qubit implementation. Imagine that you inject only one electron here. So this electron will move back, will move here back and forth. So we oscillate between those two regions. And in such a way, you can implement so-called Wannier qubit, which is position-based qubit. So quantum information is encoded, so it's spanned by two Wannier functions that are maximum localized wave functions. So there is one maximum localized wave function that is associated with quantum dot A, and another maximum localized wave function is associated with B. And basically, the standard wave function is a linear combination of those two maximum localized Wannier functions. Yes, so this scheme was kind of attempted was also proposed by Lee Karev and by Fujisawa. Fujisawa has implemented this scheme, and he was the first pioneer in single electron devices in a semiconductor. So this was around 2004. Later, many techniques and many experiments were done with PETA from Princeton and many other famous physicists. So still, this concept is also called electrostatic qubit, and electrostatic qubit has certain type of noise that is, and due to this noise, there's a big phase decoherence in a qubit. So essentially, many people has abandoned this concept, and after certain experiments, they have moved to a so-called spin-based qubit. So spin-based qubit is the dominant implementation of most current quantum technologies. I would say more than 90% of effort is done in direction of implementation of better and better spin-based qubits. Still, I'm not that much following this fashion right now. I'm still kind of focused on this position-based qubit or electrostatic qubit or Wannier qubit. Recently, there was a discovery that this was quite amazing discovery that most recent schemes of CMOS technology are preserving its properties at very low temperatures. So basically, if you have imagine you have such transistor at room temperature, you cool it down to liquid nitrogen temperature, you cool it down even further, and what turns out is there's only small change of IV characteristic in range of 20%, but essentially the functionality is being preserved. So it also turns out that because this functionality is being preserved, you can even hit millikelvin regime, and there are various attempts right now to move in this direction. So basically, there is a kind of high expectation that with such scheme as presented here, you can implement a qubit that will be operational at 4 Kelvin. So this means simply that you can only use helium-4, and that is less expensive than helium-3. That is extremely expensive. So there is a big promise that this technology will be created, and further, this technology of semiconductor qubits will be integrated with the classical qubits. All right, so there is a bunch of my work in this direction. Yeah, so obviously today I'm just not going to talk on some details, but I also have other possible topics that can be covered in maybe during next meetings. So this qubit can basically encode the block sphere, and so you can make also phase imprint on this qubit by source of Hadron vector potential, like external source, external current that flows, can make a phase imprint on this system, so you can control phase difference between quantum dot A and B. You can also control phase difference in electrical way by lowering the bottom of potential, and then there is a so-called electric Aharonov-Bohm effect. So the difference in the potential in quantum dot A and B brings different speed of evolution of quantum phase. And this, so basically, in principle, this qubit can be only controlled electrostatically. And if it's only being controlled electrostatically, it's very good news, because it can be very compact. So usually the magnetic control requires a lot of space. So basically, Transmon qubit that is being used by IBM Quantum Experience and also by Google. This Transmon qubit is using two Josephson junctions and is very spacey and cannot be downscaled, since there's a fundamental limit of superconducting coherence length. And superconducting coherence length is the size of Cooper pair. That is a pair of two. So there are basically two electrons with opposite spin are forming quasi-boson that is a Cooper pair. And this Cooper pair has this feature that, how to say, is of size of pretty much from 1,000 to 3,000 angstroms. So it's quite big. So it's from 100 to 300 nanometers. And so this is the limit on the size of Josephson junction. So you cannot downscale Josephson junction in classical superconductor for smaller dimensions, because you will lose superconductivity principle. All right, so this was just a kind of brief introduction to this position-dependent qubit in a chain of coupled quantum dots. Obviously, you can how to say, extend the scheme for more coupled quantum dots, but it's more technical issue, so I'm not going to touch this this further extension you can find in this work. Okay, so, and then there's tight binding model and Wannier qubit. So how to make the simplest description of a Wannier position-based qubit, or so this is by usage of tight binding model. So basically, we approximate that we have a wave function that is being localized only on two nodes, on the left and right quantum dot. This is psi1 and psi2. And there is certain energy that is being localized on the left quantum dot, and this is EP1, and certain energy that is localized on the right quantum dot. This is EP2. And there is some hopping term. So there's certain energy it takes place, the electron can jump from left to right quantum dot. So certain part of this energy in the Hamiltonian can travel. This is hopping energy. This is modulus TS12. And usually there is, due to harmicity of Hamiltonian, this is TS12 complex conjugate. So this is very simple 2x2 matrix that has obviously two eigenenergies and two eigenvalues. So and then you can determine the evolution of a quantum state with such matrix in a very easy way. So and obviously there is a mapping from a Schrödinger formalism to tight binding formalism. Tight binding formalism can be used as the most simple version of a Hubbard model in a way. Well, I would say this is the most simple case of Hubbard model. That's very successful in condensed matter physics. Anyway, so this prescription for a mapping is by taking two so maximum localized wave function of the left quantum dot has the name of a Wannier function, VL. So this localized energy is expressed in this way. So here is a kinetic term and potential energy term, and this is this wave function. In the same, just the same type of expression is valid for another quantum dot. So also you have maximum localized wave function on the right side, and so there is this kinetic operator and energy potential operator. So this is AP2. Obviously, in general case, it can be time dependent, but still, in static case, it can be time independent. And this is effective potential that describes that is aligned around around those two quantum dots, including the presence on those quantum dots. And there's a Hoping energy between left and right quantum dots. So this is Wannier function on the right, and this is Wannier function on the left. So obviously, since those, yeah, so we can exchange this Hoping from left to right and right to the left. So it is again the same operator in the middle, kinetic energy plus potential energy, and yeah, so this is this Wannier functions. So this Wannier function approach is a description, or the state binding model description is valid. How to say? Is valid for certain time scales. So in a sense, so in certain discrete time steps, this approach is valid. It's not valid if you take too short time step, but it's effective. It can describe your entanglement between two qubits that are interacting in electrostatic way. So in that sense, is quite effective if a scheme for modeling many interacting qubits at the same time. Yeah, and it's at this stage it's fully analytical up to, so two interacting qubits you can describe in the whole analytical way, and if you have more than two, then you use this analyticity principle. All right, so this is just a scheme of possible wave functions for two coupled quantum dots, and there is a change of effective potential. So you can recognize also among those functions the Wannier functions. So that's just a kind of very standard simulation of solving a Schrödinger equation in one dimension using Toeplitz matrix approach. It's very simple. All right, so and then there's scheme which I already described is also being summarized here. So we have this possibility of making this planar technology or even three-dimensional technology of semiconductor nanowires, and on which we place the electrodes, and then we can play with this quantum information processing in such type of system. All right. So using this type of electronics, basically we have, it's quite obvious that we have an anti-correlation principle. If you consider two charge balls into boxes, they will try to take maximum distance due to the principle of minimization of electrostatic energy. And yeah, this is being expressed by Coulomb force. So classical particles will take maximum distance. And yeah, and when you start to move to a quantum regime, then this wave function, then the presence of one particle will be spread around the whole box, but still this principle will be valid. So you have anti-correlation of positions in a case of semiconductor technology. And if you deal with superconducting technology, you have anti-correlation of currents. So there's a Meissner shielding current that is being present in superconducting technology using Josephson junctions. Still, I would say there's also, I will also expect that at small nanoscale, there's apart from the principle of anti-correlation of presence of positions, there shall be also a kind of principle of current anti-correlation, also due to similar effect. since since electric current in a semiconductor, incoherent semiconductor has the same formula as superconducting electric current, and there are both probability currents. And having such scheme, you can think about implementation of arbitrary complicated quantum logic gates like CNOT. So this is controllable. So this system of two boxes implements a logical inversion. So this zero is turned into one, and so on. And here, if you have also logical inversion, if you forget about presence of this qubit. So this is NOT gate, and presence of this third ball makes this qubit to be a controllable NOT gate. So we call it CNOT gate. In similar way, we can design our quantum gates. Right. So and also having this scheme, we can think about implementation of CMOS of implementation of a quantum artificial neural networks. And so we have a chain of coupled quantum dots their dots are being marked by a red color, and we have this connectivity between those quantum dots is being controlled by this gray color electrodes. So basically, if you inject free electrons, this is the issue of a quantum transport via this nanostructure. So you can create certain layers. So this basically, this network shall implement the quantum neural network. So this is also at the same time an body problem. And then there's open issue how you can use this quantum neural network for information processing, how you can detect entanglement of initial injected electrons, and so on. So this is topic in progress, and I'm still studying. All right, so let me move to the case of two coupled linear qubits. So basically, we have I have this details on this approach described in paper, analytical view on two coupled single electron lines. So you can refer to this paper, and basically, so we have one line, we have three electrodes, and we can make the presence of an electron to be distributed between node 1 and 2. And on another line that is in parallel, you have presence of electron at 1' and 2', and it's also 1a, 2a, and 1b and 2b. There's a certain distance between the lines. And if you write down the equations of motion in Tite-Binding's model, you have such Hamiltonian that is 4×4. So here Ts 2b, 1b is a Hoping between 1 and 2, and at this lower line, and Hoping between 2 and 1 is denoted by in such a way. So Hoping terms are of diagonal terms, and localized energy is terms are on matrix diagonal, and Coulomb, and there's interaction of node 1 with 1', or let's say maybe in that way 1a with 1b, 1a with 2b, and so on, 2a with 1b, and 2a with 2b. Of course, particle dust is not self-interacting, so there are four terms of interaction, and then when you solve this, you need to find eigenenergy and eigenstates, and you will find that this quantum state is being ground state is more complicated. It's a superposition of, so in classical physics, the ground state is one electron is either localized here and another is here. So there are at maximum far distance. In a quantum case, there is a superposition of this case and this case. So obviously ground states of a classical and quantum system are different. So what is quite natural here is that due to a presence of electrostatic interaction, there is emergence of entanglement, and this is quite automatic. And yeah, so in a sense, everything. So here we don't really consider spin degrees of freedom. We only consider this this electrostatic kind of entanglement. Obviously, it will be more complicated if you also turn on the spin degrees of freedom. So basically, such type of states. So you can write down the presence. Yeah. So there is so essentially there are four distinct states. The presence of a quantum node at 1 prime is denoted by P1 big capital. Then there is a P1 2 prime. This is P2. So a 1 electron is present at 1 second at 2 prime. Then you have the third case, the presence of 1 electron at node 2 and another at 1 prime and 2 2. So there are four possibilities expressed here. And then you have evolution of the system with time. So first noticeable feature is that the model as given here is quite similar to epidemic model, except the fact that there is square roots of probability, not a probability, right? If there is a probability, not a square root of probability, if you drop this phase term and forget about this, yeah. So this is so you feel that there are some similarities, but there are some differences. So now I will try to just show very simply how to make a mapping from one system to another system by very few elementary steps. All right, so what are the steps? So basically, if you have epidemic model, classical epidemic model can be written in such a way as equation 8. So you have matrix acting on P1 and P2, and the result is d over dt and P1, P2. So first feature which you can say is that yes, such model can incorporate superposition of two distinct states, but there are some subtle differences. So first of all, so you can also basically, in principle, you can find a kind of energy terms to eigenenergy terms, but you have to be careful because probabilities are only positive value or zero value; they are not negative value. So you need to find this probabilities in such a way that so you can expect the presence of a superposition, but only to a certain, probably not in such broad scale as it takes place in a quantum mechanics. Still, if you write down this part in terms of, instead of P1, you write square root of P1 times square root of P1, you end up in such term. And then we make a comparison. So these are equations of motion for classical epidemic model. And in quantum epidemic model, the equations of motion are as following. So we have, yeah, again, there are two eigenenergies, but still what is prominent here is that, yes, this is 2 by 2 matrix with two localized energies, AP1 and AP2, and there is a hoping term. This acts on the quantum state that can be expressed as square root of probability times some phase factor. And the result of this is this action of imaginary unit times Planck constant d over dt on this quantum state. And if you write it down very simply, this quantum state in such a way as given here, yeah, you can arrive to a such expression that is here. So essentially you will have expression where you have d over dt square root of probability. And then we can make a next step. This is very simple step. So yeah, so basically, so the deal is that we have this matrix 2 by 2, and yeah, I'm just trying to see if I didn't make any. Yeah, and then so first thing is you want to get rid of these phase factors. So you multiply both sides by this diagonal, by this diagonal matrix. So, and yeah, I'm just thinking if I didn't make any deeper mistake when I just write the slides into quick way. Yeah, so forget about this term. So basically you have such equation as given here. Just forget about this term. So you have such equation as here. And then your problem is that you have this d over dt, and you have desire to have just p1, p2. So basically, how to solve this problem? So you multiply both sides by such another diagonal matrix of such shape as given here. So what happens is on the right side, this right side will become d over dt p1, p2. So you have such matrices, diagonal matrix. And the problem is that you have here, this is p1, p2, and this still acts on the state. There is square root of p1 and square root of p2, and there is there are two phase factors. But there's a way to deal this with, I will show on the next slide. So on the next slide, what happens is I'm placing just here, multiplying by identity matrix that is written in a tricky way. So here I write p1 a to minus e phase factor and p2 e to minus phase factor. And obviously I need to make an inverse terms, so those two matrices will compensate. So basically what I have achieved is I have achieved the equation of motion d over dt p1 p2, and that is equal to, if you take this term, this will be the same as here, p1 p2. So basically I have, so there is such matrix that acts on such state. So I have shown that there is a unique mapping from quantum mechanical picture to classical epidemic model, and this exercise can be how to say, we can make it more, we can extend this reasoning. I will just for a second, I just need to open my this recent yeah, just give me a second. So this is my archive paper. Yeah, so basically this is this paper. So far I only exercised the simplest variant, but basically okay, so my central message is that I can have all features of qubit state that is expressed by tight binding model, classical or a quantum tight binding model, and I can map all these features to a classical epidemic model. So I can also have, so I can have this Rabi oscillations between two, between two eigenenergies. So I also can find the eigenenergy in the case of epidemic model in certain ranges, in certain set of parameters. So basically I have everything that is, I can have also quantum entanglement. Give me a second, so I will just briefly describe the quantum entanglement. So yeah, so basically there is a weak measurement, so you can have two cities that are being infected, and there is dynamical transport between them. There will be a quantum entanglement. Give me a second. So yeah, so this is so how we are dealing with that. So basically we need to rewrite two. So at first we consider two non-interacting cities having only two states, and in very similar fashion in quantum mechanics. And then so basically in epidemic model, at first we consider non-interacting two non-interacting cities that can be incorporated by such matrix 4x4. It has such structure, but if the structure is being perturbed, the system already becomes interactive. The cities start to interact. And what is interesting is that, okay, there's a lot of technicalities, but everything is basically the same as in quantum mechanics. So what is essential in this approach is that, so how to say, it's better to make this mapping using. So far I just described you the mapping between. So the epidemic model that was created was 2x2, and the tide dividing model was 2x2. But you can make a better mapping. So when you map 2x2 tide binding Hamiltonian into 4x4 epidemic model, and then you will distinguish two different probabilities for occurrence of a real value of wave function and imaginary wave function. Yeah, so this is in such a way, you can say that epidemic model is nothing else as demonstrate. So basically you can exercise this on a greater scale. And so you have also a Harlamov-Bohm effect present in a classical epidemic model. You have Rabi oscillations. You have also entanglement. So I'm asking what's the difference? Oh, there are some differences, but not so. There are less differences than initially assumed. Yeah, so maybe just to show you maybe the last case of mapping these two interacting qubits and the result of this mapping. So since this is very technical, I just want to jump to this conclusion. Yeah, it's a bit lengthy paper, but anyway, sorry for that. Yeah, so there is a mapping. So basically, 2x2. So there is matrix 8x8, where I have this. You see, I take two parts of probabilities: a real value and imaginary value, and basically, I also extend the tide binding model. So the tide binding model which I have is, in general case, is I can also put dissipative terms. So AP1 energy will have a real value and imaginary value, and also this matrix doesn't need to be Hermitian. So basically I have unique mapping. So I'm saying that if you limit ourselves only to tide binding model, I can so any system of coupled qubits, electrostatically coupled qubits, can be any system of electrostatically coupled qubits can be equivalent to just that. So this system of coupled qubits that expressed by matrix n by n can be mapped to matrix 2n by 2n in epidemic model. All right, so I would say, and very last thing is our equations of motion. So basically we can use the same measure of entanglement. We can use von Neumann entropy concept in a quantum mechanics, how it can be achieved. So basically this okay, let me move to this case. So basically, first there's only one essential difference, because here I call it matrix S acting on state P1, P2 is use d over dt with the same as classical state. So what I need to do is that, so the essential for this concept of von entropy von Neumann entropy is that I'm dealing with matrix of square root of probabilities. So what happens is that so in classical physics I have Hamiltonian acting on the density matrix of classical state, but here there is anti-commutator. There is an anticommutator, and it gives me equation of motion, d over dt, with a density matrix of a classical system. But in quantum mechanical system, they are almost the same equations of motion, and there is d over dt and this one. But the difference is that I have this anticommutator. Commutator. So there is commutator and anticommutator. And the difference is that in the classical equations of motion that arise from a classical epidemic model, there is no imaginary time times Planck constant. Actually, Planck constant we can engineer if we really want, but there's no this imaginary term. So those equations of motions are a bit similar, but still different. And there is one more feature, and this feature is basically that I would say, right. This feature is that there's a probability with normalization of state if we have a classical epidemic model. So this sum of P1 and P2 does not need to be 1, but I would say it's not a problem because only what matters at this stage is the ratio between P1 and P2. So in that sense, so this state evolution of state of that arises from classical epidemic model is not normalized, but doesn't really matter in that context. All right, so I guess that's the essence of my presentation. There are some questions. Maybe Jacek, could you please give me some questions?
Can you hear me well? Is that?
Yeah.
Okay, great. So it was a very interesting presentation, although pretty far from what I'm currently doing. But I was really hoping to see, when you mentioned the classical epidemic model, I was thinking about epidemic models that really deal with populations of infected, of recovered. And, for example, the classical SIR model. It would be, I think it would be pretty interesting to see a possibility of application of your results into those Markov-based or SIR-based models. Maybe you can get better results, or your results can be at least improving the existing ones.
Yes, sure. I mean,
where is this epidemic part? I simply maybe I'm simply confused. Where is this epidemic part here? That is, you are mentioning briefly, let's say, 2 cities with the population of infected and susceptible and removed, but we are not seeing, for example, classical things that are expected in epidemic models, like forecasts, like estimates, like simulations. Do you think you can get those from your models?
Well, sure. This model. So basically, what I called epidemic model was a matrix, a real value matrix, square matrix, acting on a vector that has probabilities, right? P1 to Pn. And the result of this action is time derivative that is acting on the whole vector of probabilities. So this was definition of epidemic model from my point of view. And the issues which you are mentioning, sure, they can be done. So what I'm saying is that so my message is very simple. Any classical epidemic model that is, you collect data, you build this S matrix. Because I would say that the most essential for this classical epidemic model is this matrix that acts on this probability vector, P1 to Pn. And once you have it, I can uniquely map you this to quantum mechanical model. So basically, I'm saying that you can somehow have this view on the data, on the classical physics data, also in a quantum mechanical picture. You can and both ways are possible. I was simply thinking, how to make quantum mechanics less mysterious than most people think. And so this is in the spirit of Jarek Duda seminars on the foundations of quantum mechanics. basically the central expectation is that quantum mechanics is not that fundamental as people think, and then yeah, so there is I would say there are various yes, so there is maybe Jarek Duda, can you make a comment? That would be great.
So it is quite close from my interest, but so MERV is quite similar. So it's random walk based on maximization of entropy or just uniform or Boltzmann path ensemble. So this is like random walk inside Ising model MERV, and there are lots of papers for various social models. I have just linked some epidemiology model. So maybe I think this might be quite connected, but I have to admit I also have a problem with understanding.
So do you think that my model is equivalent to MERV model?
So MERV is just uniform or Boltzmann distribution of paths. So like treating one-dimensional Ising model as a random walk. So this is classical. MERV is just probabilities is purely classical. Only non-negative probabilities.
Yeah, I'm still thinking to what extent the considerations conducted by me are equivalent to this MERV model. In any case, I get probably the entropy dependence with time I can obtain. So since I have this density matrix approach for classical epidemic model, I can get entropy with time. So yeah, so perhaps
MERV maximizes not entropy as entropy in given moment as for stationary probability distribution, but entropy rate. So this is the average of entropy of step with weights of probability distribution of the state. Mm-hmm. So the sum probability of I times entropy Shannon entropy from position I for one step.
Mm-hmm. Mm-hmm. Yes, so this was, because this is just the beginning, because actually, since I have a mapping of Schrödinger equation to tight binding model, and then mapping from tight binding model to epidemic model, in principle, I can, I have a very practical question for myself, how I can design the quantum machine learning algorithms, and if I can treat, so basically I claim that I have this theory of stochastic finite state machine for a chain of coupled quantum dots. And then I can engineer these probabilities in a way that is desirable. But yeah, so what do you think about this probability superposition, Jarek? What do you think about this probability superposition in epidemic model?
I don't know. I don't know. So it's very abstract model. So I cannot connect it with epidemiology. It's difficult for me to connect it with epidemiology.
Mm-hmm. I see. All right. Yeah, I will continue this topic. This was just a flavor. I'm sorry that I made such short number of slides. I hope I could be able to do more, but still, you see that the chain of mathematical steps which I made is very simple. This is very simple algebra, what I did. So I just simply, I see really a lot of features of a quantum mechanics in epidemic model, which basically encodes classical physics. So in that sense, it's I would say quantum mechanics is not that novel as people would think. since I have so basically what I have managed to identify, the entangled states in classical physics. I get entangled states in epidemic model. I have prescription for this entangled states entropy with time. It's a bit lengthy, but so this is my. So what you see here is the case of two interacting cities. This is density matrix with time, what I have. So this is evolution. Exponents are evolution. And this is density matrix at initial time. So I have this prescription for evolution. And obviously, then I need to reduce the sizes of these matrices. So in any case, having such density matrix, I can get reductions. I can get two partial density matrices, and then I can compute its. I can normalize them, and I can compute von Neumann entropy. So I'm using concept of von Neumann entropy that is taken from quantum physics. I'm using this for a classical epidemic model, and so this is a novelty. I'm saying that you don't need to go to extreme low temperatures to get a quantum entanglement, and you don't. Yeah. So also I can encode various type of quantum gates in a class using just classical epidemic model. So that's a novelty which I claim to have, and yeah, perhaps I will continue this topic on some future possible meetings. I need to rewrite this manuscript probably and make some more slides and extend more. Yeah, so make more analogies. So perhaps I hope that you will buy my idea at least. There's also possible. Yeah.
Please take a look at the Merv paper, because I think there are lots of similarities.
All right. Okay. I will. Okay. In most radical version, there is also. I didn't have time to describe this. There is. Sorry for that. There is the case of. Yes. So this S1 matrix is obtained from two coupled Wannier qubits that have dissipation. So basically, I get this prescription how to get this. So yeah.
Gentlemen, I have to apologize, but I have to leave. So thanks a lot for
All right.
discussion.
Thanks.
Bye-bye.
Bye-bye. So are there any other questions or remarks? So what I just want to underline is that I have two interacting position-based qubit, and I obtained 8x8 matrix, and I can get dynamics. So I basically have two values of probabilities. So one is so there is cosine theta square p1 and sine theta p1. So two different probabilities. So basically, I get also phase dynamics of a quantum system. So I don't see how I see that I have no loss of information if I make such mapping. So